Hey guys, so this is a video on part 2 of Unit 8, the check-in after you have done the Khan Academy things. This would be a great video to check in on your understanding of that material, and also the video on the sine and cosine notes that I posted earlier. This is it flows from there as well. So before I get started, I have a couple of people who wanted to say hello. But this is awkward because they're going to have to put their heads underneath this camera. So I'm going to let them do that so they can go back to what they were doing. Okay.
Hi.
Okay, that was just your eye. And okay.
No,
okay, come on. Nobody. Okay.
Hi.
There we go. That was great.
Hi.
Okay, that was just a blur. Okay, great. Thank you guys. I'm sure they appreciated that saying hello. All right. So let's get started with this. Again, as I've said before, I think that it would be best if you printed this out or looked at it from your computer and tried it all first and then watch this video. So if you have not tried it for yourself first, please pause and do that before watching this. All right. So number 1. We've previously discussed a Ferris wheel, the radius of 20 feet, whose center is 25 feet off the ground and completes one counterclockwise revolution every 30 seconds. That is what the video was that we started with before the Khan Academy. The equation that we use to represent the height of the passenger at any given time t, if you recall, was height equals 20, that was the radius, but it was also what we call the amplitude, how high we could get, sine 12t, and remember the 12 was interesting because it was not, well, there's no 12 in any of these words, but we were able to calculate how many degrees we would go every 1 second, and that was 12 degrees, and so that's why that shows up here, 12 degrees per second. And then, of course, plus the 25 is simply to take into consideration the center of the Ferris wheel being 25 feet off the ground. And we talked a lot about positives and negatives and when sine was positive and when it was negative and all of that. The graph that we ended up graphing, if you recall, where this was time and this was height, remember my helpful hint for graphing these things was to start at the very beginning. So at time 0, we said that we were, even though it was kind of strange, we thought of the Ferris wheel as starting right here. So we were 25 feet off the ground at time 0. When we went all the way around, which took 30 seconds, we were back at that height. When we were halfway around, which of course was 15 seconds in, we were also at that height right here. And then in between the beginning and halfway through, we reached our highest point, which, because the radius was 20, was 20 above medium, which would get us to 45. So halfway in here we were at 45, and then of course halfway between here and here we were at our lowest point, which would be 20 below this at 5. And so we plotted our 5 points, and we were able to make our smooth curve to get our graph of our height over time. Okay, so questions 2 and 3 I think are really good kind of summarizing questions of what the equations look like, what the graphs look like, and how we can do this forever with any of these numbers changing or whatever the case may be. So the equation, let's get the general equation written down here so we can talk about the changes in it. Typically, again, we talk about this as being our equation. And remember, the C is not there because the C is a phase shift left or right, which you will not talk about until pre-cal. So we can leave it out now. Okay, so how would the equation change if the radius was smaller or larger? Of course, we noticed that the radius showed up here right in front of our equation every time. So the equation would change because A would get smaller or larger. A would be larger if the radius was larger because I would go up further on the graph. that thus affecting the amplitude, which we said was the distance that we go up or the distance that we go down. So this is the amplitude here on the graph, and that's the amplitude on the equation. So that's how that would change. How would the equation change if the height of the center was greater or smaller? Of course, that height of the center is what we kind of had to add on to the end every time to kind of tell us where we were in relation to that midline, that midpoint. And so D would change based on that height changing. So here it is on the graph as well. We go up and we go down. We perfectly go up and down. It's symmetrical. It's beautiful. It's always going to stay that way. And that's how we see that. And then, of course, the wheel rotates faster or slower. So if the Ferris wheel is going faster, we'll say, then we are going to be able to get through the cycle faster. It'll be smaller than 30 seconds for sure. So in the equation, of course, that would mean that our angular speed, which is right here, this B, which is angular speed, that would change. That would mean that I'm able to cover more degrees in a second, of course, if I'm going faster. What that means for us in the equation, of course, and how that relates to our graph, that this is the big connection that we need to make. Remember, B does not show up directly on our graph, but the period shows up on our graph. The period being how long it takes to get through one cycle. And remember that the period is directly related to B. A period is 360 degrees over B. So if I take degrees divided by degrees per minute or degrees per second or whatever the case may be, that's going to leave me with minutes or seconds, some sort of time. In time, of course, a period is telling you how long it takes to get through the cycle. So I should end up with units that look like time. So that is that relationship. Now remember, when we work in radians, which we will often do, you will certainly do a great deal of in pre-cal, this equation will not be 360 degrees over B. Instead, this equation will be 2 pi over B. Because remember, 2 pi in radians is the same thing as 360 degrees. So just keep that in mind. Okay, kind of already answered number 3 a lot in what we just did, but just to be very specific here, how would the graph change if? So if the radius of the wheel changed, we said that the amplitude would change, which would mean that, I'm going to write this down here, the amplitude of the graph would change, which is kind of like a vertical stretch or shrink. You think I'm not going up as far, then my graph might look, smaller. Or if I'm going up even more, then that amplitude is going to make the graph longer, vertically stretching it. So that's how that's going to show up on our graph. The height, of course, as we talked about being this D value, as we talked about here, that's just going to change what we call the midline. We also call it the equilibrium. It's the line that you go above and below. So that would change if that would be the D value that would change, and that would be the value that would change here on our graph if the Ferris wheel was at a different height. Okay, and of course the wheel rotates faster or slower. That of course changes our angular speed, which doesn't show up on our graph, but as we just discussed, that would change the period of the graph. So that, changing the period of the graph, would be like a horizontal stretch or shrink. So you can think about, does that mean that the graph is going to take a lot longer to get through? Or is the graph going to be done really, really, really quickly in a certain amount of time? So that is how those things would be affected. And you can see that in your equation, you can see that in a graph. And there you have it. That's a big deal right there. Okay, so moving up. Question 4, some examples here of different situations, different looking Ferris wheels. Can you take all that information that we just kind of discussed and can you put it together in a new equation. So 4a, the radius of the wheel is 30 feet, the center is 45 feet above ground, and the angular speed is 15 degrees per second, counterclockwise. Okay, so again, you're taking all that stuff we just talked about, where these numbers show up in an equation. And so, of course, this would be 30. Of course, I'm going to use sine because I'm still talking about the height of the rider. So I'm still using the sine function. If the angular speed is 15 degrees per second, that is the b value. It's right there in the information. 15t, b is the angular speed, and then of course 45 feet above ground would be the 45. Now, if I wanted to graph this, which it doesn't ask me to, but if I wanted to, remember, this would show up on the graph, this would show up on the graph, this would not show up on the graph. Instead, the graph, I would have to say that the period is 360 over 15, which would be 24. So that would mean that the time in between the start and the end would be 24 seconds or 24 units on your graph. That is what would show up on your graph. Okay, B, the radius is 50 feet. The center of the wheel is at ground level, so you spend some time below ground. Interesting. And the wheel makes one revolution clockwise every 15 seconds. A lot of things are going weird here. We're going underground. Strange. We are going clockwise, which means that when we get on the Ferris wheel, in our bizarre place that we get on these Ferris wheels, which is here, instead of going up and around like this, we're actually headed down first. So we get on and we're directly underground immediately. So let's think about the things that we do know. I can say y equals or h equals for height or whatever. The radius is still going to be right here, 50, of course. Still a sine function, of course. This, if I'm told that it makes a revolution every 15 seconds, then that means that the period is 15. So, of course, 360 over the period would give me the angular speed. So that would be 24. This time would be the angular speed, 24 degrees per second, t. As far as my plus anything here, well, if the midline is the ground, if I go halfway or underground and then halfway not, then this is just going to be a plus 0. So I don't need to write that down. That'd be silly. One last thing, though, this clockwise thing. If I want to turn the direction of my graph, if I think back up to this graph here where I go up first, that's what sine graphs do. They start at the middle, they go up, and then they go down, and then they come back. So if I wanted to go down instead of up first, then that means I'm going to have to flip my graph. I'm going to have to flip it horizontally. And we should all know from our transformations that we've talked about quite a bit this year, if I want to flip something over the x-axis, flip it over and have it going down and then up, then I'm going to need to put a negative right here. And I know that a lot of you in your homes just now were like, put a negative at the beginning. Yeah, that's what you do, before I even said it. So, good job. All right, moving on. Number 5, we are given an equation, we are asked to find stuff, and then graph it ourselves. Obviously, this will be a big deal for you in calculus without a calculator, or in pre-cal anyway, to be able to graph this all by yourself with the information that you're given. So here's the equation, very similar to what we've seen before. Amplitude, of course, right here in front, 5. Period, remember, is not this value, but this value tells us. 360 over b is 180, so 180 is the period. And then the vertical displacement, I will call that, or you could just write vertical shift or whatever you want to do. That would be 4, so up 4. All right, didn't leave myself a great deal of room here, but let's graph this. Remember, when we graph, we don't have to be, I don't, in fact, want you to spend time making little tick marks for every little value. I want you to put the key points on the graph and then connect them in a smooth curve. So, I start at 0. I know that at 0, I'm going to be at my midline. So my midline looks to be 4, so I'm going to put a 4 right here. This is where I start. I then put my ending point, and I know that I'm going to end this thing 180 units over here. So at 180, I'm also at 4. Halfway between, at 90, I'm also at 4. Halfway between here and here, I'm at my highest point, which of course will be 5 units above the middle. So that is at 9. 4 plus 5 is 9. So right here, you can label that as 45 if you want, but I'm up here. In between here and here, I am at my lowest point, which would be 5 below this, which of course would be -1. And so there you have it. Please don't make these graphs pointy, they're not pointy. There is the smooth curve. That should look very similar to that. I didn't do a great job graphing that, but. So there you go. That's how you would graph a sine graph. All right, so let's flip over. Notice, and this is where some people do, you're going too fast, get a little confused here. This is actually a cosine graph right here. So cosine graphs and sine graphs have a great deal in common, as we talked about before, but not everything. You would have to graph this slightly differently because it is a cosine graph. We can still find, though, the amplitude to be 2. We can still find the period to be 360 over 15, which is 24. And the vertical displacement we know to be -1 based on our equations. All of that should be pretty easy to identify at this moment. All right, quick sketch of the graph here. Okay, since this is a cosine graph, I need to remind myself of what a typical cosine graph looks like. And a cosine graph does not start at its midpoint. It does not start at the midline, the equilibrium. It actually starts at its greatest point. So a cosine graph, if you recall, does a little something like this. So it starts at its max, ends at its max, and halfway through it's actually at its minimum. So let's keep that in mind and not graph this like a sine graph. All right, so if the amplitude is 2 and the vertical displacement is -1, then this -1 is kind of our line that we're going to be oscillating around. So 2 above that, of course, would be at +1. So that is where we begin our story. 24 units later, I'm going to be right back there. Halfway between 12, I'm going to be at my lowest point. That is a loud verb. So if that is middle, this is the middle, and the amplitude is 2, then I'm going to go down 2, which would put me at -3. And so that is my lowest point. At 6, I'm going to, of course, be at the midline. Same thing over here. And so I can draw one cycle of that as well. So, of course, this would keep repeating and so on forever. But this is just one cycle of it. Alright, so that is basically as hard as that is going to get with graphing. Until pre-cal, when you add in the C value and you have to shift, you'll just be starting in a different place horizontally. Instead of starting right here, somewhere here, you'll start somewhere else horizontally. Okay. So, number 7, kind of going backwards. Here is the graph, and you are to write the equation. So when I look at this graph, the first thing I need to decide is, do I feel like this is a sine graph or a cosine graph? And that'll actually be kind of a silly question in pre-cal because of what I just said. It can be either. The way we are talking in Math 3, though, this totally looks like a sine graph. Why do I think that? Because it starts at the midline. At time 0, I'm right here at the middle. If it had started up or down somewhere, then I would consider this a cosine graph. But just for those of you who are ready for this, when I get to pre-cal, I could actually see this as a cosine graph that is shifted, since this is 2, 1 unit over. And so I could think, oh, it's actually a cosine graph that starts over here. Okay, but but I don't need to do that right now. I'm going to think of this as a sine graph. By looking at this graph, I can clearly see the amplitude. Up and down, I go the same up and down. I go 2 units up and 2 units down. So 2 is the amplitude. This is a sine graph. I'm not going to add anything over here. Plus 0. We can see that the midline is 0. So the question now becomes, what is B? Remember, B is not on the graph. The period is on the graph though. I can see by this graph that it takes 4 units to get the whole cycle done. So the period equals 4. So 360 over 4 is 90, which means that the angular speed must be 90. And so there is my equation. Okay, last couple of questions. Number 8, given that the sine of theta is -4/9 and theta is between 180 and 270 degrees, find the cosine and the tangent. Okay, again, pictures are incredibly important here. You must draw your picture because you got to make sure you're in the right quadrant, and you got to make sure that you are drawing the triangle correctly and labeling the parts of it correctly. So if I'm between 180 and 270 degrees, then I must be here in the 3rd quadrant. Remember, your angles always involve the x-axis, so that would mean that this is my theta that I'm talking about. This is the angle theta formed from a line, x-axis, moving around the circle. Sine, as we know, is opposite over hypotenuse. So if the sine of this is -4/9, then opposite's -4. Hypotenuse must be 9. Remember, the hypotenuse is always positive. So of course, looking at this picture, I'm certainly glad I drew it. I know that it is a right triangle, and I know that I can find this missing side over here by using the Pythagorean theorem. So if I do 9 squared minus 36 squared, and take the square root of that, of course I get 65. But, and here is the key, the reason that I drew this triangle is so that I could easily see that this square root of 65 has to be negative. I know it's negative because it's over here. It's going that direction in the 3rd quadrant. If I miss that SIGN sign, then everything is ruined. So that's why you need to draw those. Every single year I have people think I don't actually have to draw those. I don't actually have to put them in the right quadrant, and they end up missing the problem because of an SIGN sign error. So don't do that. Don't be one of those people. All right, so now that I have a triangle, this should be pretty straightforward. The cosine of this angle that I have here is, of course, -√65/9, adjacent over hypotenuse. The tangent, opposite over adjacent. -4 over -√65, of course, negative over negative would be positive. Now, just so we can talk about this, there are lots and lots of people who think that this is not okay, that the square root cannot be on the bottom, and most of those people are math people. They like to rationalize. I'm sure you've heard of that before. They don't like to leave a square root on the bottom. So to fix that, they multiply the top and the bottom by the square root of 65, leaving us with 4√65 over, and of course, √65 times √65 is just 65. So most mathy type people would say this is the final answer. Most sciencey type people don't bother doing that. They don't bother rationalizing. They just leave it alone and go about their business. So just know that you know, it depends on the teacher, it depends on the situation, but you should know how to rationalize and when to rationalize. When you have a square root on the bottom, you multiply the top and the bottom by that square root, then it gets rid of the square root on the bottom and puts it on the top. So just be aware of that. All right, last question. Given that the sine of theta is 1/2. Okay, so let's draw a picture of what that would mean. If the sine of theta is 1/2, sine of theta is positive, we would say, then the sine, the height, as we've talked about it, is positive. here and here. Those two quadrants. So if the sine of theta is 1/2, we could go even further into this, and we could say that that would mean opposite over hypotenuse. And we could actually get our calculators and find this angle, of course, by doing the inverse sine. Now this is actually a unit circle value, and actually in a couple weeks we're going to talk about the unit circle, and you will use the unit circle like crazy in pre-cal and calculus. So by the time you get to that, like a year from now, if you see that, you are going to know that that is 30 degrees. Like you're just going to know that by heart. But right now you don't, which is fine because we know how to get an angle by itself. We know to take the inverse sine of both sides, so that would mean that we would do this in our calculator. Take the inverse sine of both sides, and when you do that, you get 30 degrees. So it says find a value in quadrant 1 that satisfies this. Well, that's 30 degrees. Your calculator only answers you here and here. So your calculator isn't going to tell you this value. And you'll talk more about that in pre-cal, what you do about that. Probably figure it out right now, but your calculator only tells you this value right here. This is 30 degrees. If you take the sine of 30, you get 1/2. So there you go. So it says find another value that has that same information. Well, this is where you're going to talk about that symmetry that we started this whole thing off with. And you're going to think about the circle and how it's 360 degrees and how half of it's 180 degrees, and you're going to use that picture to help you out. If the sine or the height is 1/2 here, and we drew this value over here, if this is 30 degrees, then that means that this must be 30 degrees too. If we talk about our angles as coming from the positive x-axis up and over all the way around, if half of the circle is 180, and this little piece right here has to be 30 to match up with this 30, because these are equal triangles, same height, then that means that this must be 180 minus 30, which is 150 degrees. And that should make good sense looking at this picture. 30 degrees, let me draw this picture because I've drawn all over it. 30 degrees here, 150 degrees. These should be the same, and these should be in the same place, and they should therefore have the same height, and therefore have the same sine value. So that's how you would get that. Find a value not between 0 and 360 that satisfies this. Well, you can go around a circle as many times as you want, over and over and over and over and over again. So if I'm right here at 30 degrees, and I have a height of 1/2, then all I've got to do is go around the circle again. Circle is 360 degrees. So if I take 30 and I add 360 to it, I'm going to end up right where I was. Think about that Ferris wheel. You just keep repeating the same heights over and over and over and over again. And so 30 plus 360, 390 degrees, I would actually be at that same place. So therefore the sine value would be the same. All right, and then the last question, find a value between 0 and 360, so one time around, where the sine is negative 1/2. Okay, so think about that symmetry. If this little part I've put here is 1/2, then this would be negative 1/2. If this has a height of 1/2, then this would have a height of negative 1/2. Beautiful symmetry going around there. So think about your circle. Just use the common sense that you have about 360 as being a full circle. If I want to identify this point right here, all the way around is 360. This we've said must be 30. That's 30, that's 30, that's 30, that's 30. All these are the same triangle, just cut and pasted, flipped around. So then this must mean that this is 360 minus 30, which would be 330 degrees. This must be 180 plus 30, so that would be 210 degrees. And again, I could do this all day. I could go around the circle, I could go backwards and have negative angles, which we'll talk about later. But that is the gist of what you should know. This actually came from both a review and a quiz that we would have given you in normal circumstances. So this is what you're responsible for knowing at this point. So please let me know if you have any questions about this. The next thing up for you to do is a modeling worksheet, and I'm going to ask that you complete a Google form, just letting me know that you have completed the worksheet, you've checked your answers and asking any questions on that form. And that's how I'll give you your kind of credit for your assignment next. So please make sure you take care of that. And please let me know if you have any questions or concerns at all about anything. All right, thank you guys. I miss you all. Take care.